Okay, now we reach part 3 of session 7, which was called creating custom AXI Master Peripherals. This is a kind of practical session in which I do simulation on my, in fact, AXI image rotator IP, and through simulation I want to make sure that my image rotator controller, the module that I talked about in the previous session, I want to make sure this module is correctly working. And then we go ahead in the next session with a practical implementation on the Z board. This simulation is extremely important because it allows you to find the problems with your design before you go into real hardware. So if you have, in fact, piece of IP block or something that you need to interface to, and that piece of IP does not have any model, any functional model, it's always a good idea to create a functional model yourself to at least have a small amount of simulation that usually helps to find a large number of bugs in your design. So here is the block diagram of the design once more: AXI slave block, AXI master block, and that is image rotator controller. This guy is the module that we have written for our IP block, and then later we will add the ILA when we go to the real hardware. So I want to show you the hierarchy of the design. I want to show you how each piece of the design is prepared in practice, and then we go through the simulation with the Vivado environment. So here what I have is the HDL folder, and the HDL folder I usually use for keeping the RTL. And as you see here, I have several subfolders. Practically 2 of them are mine, and the rest are copied directly from the Vivado environment. So I have here AXI Master Burst V2 folder, and this is coming from Vivado. So if you search inside your Vivado installation for AXI underline master underline burst underline V2, you will find it. It is inside the data folder. So I have directly copied this piece of code into my design. It is Xilinx code, it's not mine. And then in order to have this guy functional, in order to be able to work with this guy, you also need these 2 other folders from Vivado installation: lib underline package underline v1, and then lib underline srl 50 underline v1. These guys, they are all realized in VHDL. Our design is in Verilog. That's no problem. These 2 can be very well mixed. So I have copied these guys, and then I have a folder AXI Slave Light, and this folder contains 2 files, and that is basically my AXI slave plug. And then I have a top folder, and the top folder basically contains my top level module. This one defines, which contains the constants, and then our image rotator controller, which, as I told you, is the main module that we will develop and is the most complicated piece of hardware that we have. One comment before I continue: the realization that I have here is just an example so that you can see how you can interface to the AXI Master Best IPIF block. This is not the best I can do for creating and realizing an image rotator. So if it really comes into performance and pushing the performance to the maximum possible, it can be way better than what I'm showing to you right now. But the purpose is to keep everything as simple as possible and to learn how we talk to an AXI master block and how I can really realize a module. How I can customize this design to have my own logic inside to perform my own processing. So the purpose is to keep things as simple as possible. The purpose is not really to push the performance to the highest possible, because if it comes to really pushing the performance, then there are better ways to do it, and I don't intend to really put time on that. So I begin from AXI Slave Light. We have talked about this before in other sessions. And the AXI Slave Light, I have taught you how you generate this through Vivado. So if you have your Vivado environment, you can come, in fact, to Tools, Create and Package IP, and then you go ahead and you say create a new AXI for peripheral, and then again you go ahead, and then here you can indicate your peripheral, what type of AXI interface you want to have. And here I have kept, better to say, because I have done that before and I will show you, I have just kept one AXI Slave Light plug inside my module. The width is 32. The width is not really important. The performance of AXI Slave Light is not important, since it's only used for transferring the configuration from the CPU to the hardware accelerator. So it happens only in the beginning of the operation of the module. It's not really important. And then the number of registers, I have increased to the amount that I really need for input image address, output image address, clear, interrupt, and the rest of the registers that I described to you previous session. I think I have kept this number as 8. So I need at least 8 registers so that the CPU can write to each of these 8 registers to transfer all of the information that I need to my hardware accelerator. So I have set this configuration, and then I have went ahead and generated the IP. Okay, the automated code generator of Vivado then creates these files for you that you customize to your specific purpose, and this is what I have done. The first file is this one, and this kind of top-level module for this AXI Slave plug, and what it does, it only calls, in fact, the other module. It doesn't have any logic. And then I have customized this file, and I have added my own set of ports to this design. So as you see, there are a set of ports which are added to this IP. When Vivado generates this piece of code, you see only these ports, and these ports are the guys which are responsible for, in fact, talking to AXI Light interface. So they are AXI Light signals, and these ports that you see here are those guys which are responsible for transferring data from this module, transferring the configuration information that the CPU has written to the rest of my logic. So it contains input image address, output image address, interrupt to CPU, again output port, begin operation, begin rotation. This is the signal from this module to the image controller, and whenever the CPU writes to a specific register on this AXI Slave plug, this signal gets activated to begin the image rotation operation. Then there's an input signal from the image controller back to this module, which is rotation done, and this is the signal from which this module creates the interrupt and sends the interrupt to the CPU. And then there's rotation type, again from this module to the controller. This is in fact the command, the type of rotation that the user wants to do. And then we have the size of the image. The size of the image is a number, size of the image in the X direction and in the Y direction. And I have implemented the size of the image as multiple of 120 pixels. About this again I described in the previous session. So this is the top-level module for my AXI Slave plug, and then the implementation is basically the code which is Vivado generating, which Vivado has generated for us, and I have customized that code. So if I follow how I have customized this code, as I told you, I have implemented 8 or more registers, and then I have connected these ports to those registers. So when the CPU writes to each of those registers, practically it is indicating the contents of these ports. Okay. So for example, let's follow input image address. Input image address, if I follow, I can see that practically input image address is the content of slave register 0. And then output image address is a slave register 1, rotation types, slave register 4, and the other guys other slave registers. So as you see, the customization is very simple. The slave registers and their interface to the AXI board is already there. Vivado has done that for you. All you need to do is to connect your port to the register so that you can have the content. And then there is the logic in fact, for receiving the rotation down signal and for generating the begin rotation. And then there's the logic for generating the begin rotation signal. And then there's the logic for receiving the rotation signal, rotation down signal, and producing the interrupt to the CPU. Again, the interrupt, when I send the interrupt to the CPU, obviously I keep the interrupt active until the CPU sees the interrupt and clears the interrupt. So I have used, in fact, another one of those registers as the register that if the CPU writes to that register, it will clear the interrupt. So here we see the code. The interrupt to CPU gets activated when on the edge of, in fact, the rotation down signal, which is coming from the image rotator controller, and then the interrupt will get cleared when the CPU performs a write operation to, in fact, the fourth register inside this module. So if I go to the top of the module, I have added, in fact, the addresses, offset addresses for each of these registers here, and accordingly, I have connected the signals to the registers. This is the customization that we do on the AXI Slave plug, and it really is enough for all of our needs. Okay, so I close this AXI Slave plug, and then I go up, and then I come to the top module, to the top level module. The top level module is here, and as I have described to you previously, this top level module is looking very simple. It has an AXI Slave Light plug, an AXI Master burst enabled plug, and then it has an interrupt. And one thing I want to tell you is that this can be a really high performance AXI interface, because AXI Master interface, because it's burst enabled. So it supports bursts. It's an AXI memory mapped full interface. But yet, this is not the highest performance that you can gain. Okay? So it can be pushed further. I mean, the logic can get more complicated than this, which is not necessary and is not required for this session. But if we want to really go higher in performance, then there are things to do. Okay? We can add, in fact, additional parallel transactions. We can perform reads and writes in parallel. So currently what I'm doing in my logic is that I read one block and then I write the result. So you see, I read the block, and as I'm reading this block, I'm not writing any block. So I'm only reading this block, and then I begin writing. But imagine we want to perform a copy operation. So when I'm copying the image from one location in the memory to another location in the memory, I'm probably doing a very simple operation like adding each pixel by something. Then it's not needed that we wait for the read to finish so that we can begin the write. We can have both of them in parallel. This is also true maybe if we look further, think about flip operation or even a rotation. Okay? But at the moment, the AXI Master plug that I have here, I'm either reading from it or writing to it. And I don't intend to perform these two tasks in parallel. It's possible the logic will get more complicated, and I think it's not needed for this training session. So I have AXI Slave Light plug, AXI Master burst enabled plug, and then I have the interrupt to the CPU, and these are all of the ports that I need and I have. Now, if I go ahead, in fact, through the implementation of the top level, here I have the instantiation of my AXI Slave plug. We looked at AXI Slave plug together. We have just instantiated that block here. And then here I have the instantiation of the AXI Master Best IPIF. And this is kind of interesting because when you instantiate this block, you also indicate a set of parameters. When you instantiate this block, you also indicate a set of parameters for this AXI Master Best. And these parameters can affect the performance of your AXI Master Best module. So here you can, in fact, define the address widths, the data widths, and the maximum burst lengths. Okay, so the maximum burst lengths can really affect your performance. So try to keep it a big number, maybe 128, maybe 256, depends on the system. And obviously depends on the size of data that we transfer during each transaction from the user logic to the IPIF. But this is kind of parameter that can affect your performance. The native data width is the width of the bus between IPIF and your block. The address pipe depth is not at the moment important. And then another parameter that can really affect the performance of your design is the length width. And that is indicator of, in fact, the maximum size of the read or write transaction that your logic can ask from the IPIF. So currently I have indicated the length width to be 20. This means that the length width will be 20 bits. And this means that I can ask the IPIF to transfer for me blocks of up to 1 megabyte. So the bigger, in fact, this 1 megabyte is the maximum possible. And in our implementation, it's not really needed because the maximum size that I transfer every time is only 240 at the moment. But if you want to transfer big chunks of data, this is a parameter that you want to play with. And again, this burst length is another parameter that you want to play with. Okay? So if you want to maximize the bandwidth between your hardware accelerator and the PS, then there are also other parameters to play with inside the PS, such as qualities of service parameters and things like that. But with a good implementation here, you should be able to really get a good bandwidth for data transfer between the PS and the PL. And now, after, in fact, defining these parameters, we have a set of signals. They are the famous AXI Master Memory Mapped signals. We have talked about them a lot. And then we have another set of signals, and these are again the signals between the IPIF and our module. So if I follow these signals inside my design, I have just connected these signals to the next module that I have instantiated here. The next module is kind of the most important module in this design, and it's called Image Rotator Controller. And so if I look at Image Rotator Controller, it has two sets of signals connected to it. First, the signals between the IPIF and the logic. These are the signals that we talked about in the previous session. And then these guys, which are basically parameters of the rotation task, and they are coming from CPU, and basically they are connected to the AXI slave. So this is the module that we want to talk about a little bit and to see inside together. And then there is a point that I want to tell you before I go inside this module, and that is about the simulation. So if I go back to the presentation that I had in the previous session for you, what I told you was that if you are you have access to the ZYNQ virtual simulation environment of Cadence, or you have models of the PS somehow, or you have access to bus functional models of Xilinx, you have the license, you can provide them, then maybe it's a very good idea to add them to your simulation environment and then simulate your hardware accelerator along with the bus functional models that Xilinx has provided. But here, for this design, what I have done is the simplest we can do. And as I told you, that is to realize models for the AXI Slave and AXI Master plug. So I have developed two Verilog models. That one for the AXI Slave plug is extremely simple because the AXI Slave plug is really simple. I don't think ever we will have bug there. But the one for AXI Master Burst, the model that I have developed is slightly more complicated, not that much. I have tried to keep it as simple as possible. And with this set, I performed the simulation to validate the correct operation of my design. Okay? So if I look at my top level implementation, if I look how I am instantiating this AXI Slave plug, I see a point. And the important point is the following. If you look at the top level code, you will see that the AXI Slave plug is instantiated 2 times. One time, the instantiation is the instantiation of the model. Another time, the instantiation is the instantiation of the main module, which should be synthesized. So how I am doing that is through a very simple if-def. I say if-def, this is a simulation only, instantiate the simulation model for AXI Slave plug. Otherwise, if this is not a simulation, instantiate the full RTL that we have for the AXI Slave plug. And same as this one, for the AXI Master plug, if this is only a simulation, instantiate the model that I have developed myself for the AXI Master plug. But if it is synthesis, then instantiate the main Xilinx AXI Master Best IPIF. So at the time of the simulation, my models are active. At the time of synthesis, the original Xilinx AXI Master Best IPIF is active. Now, how do I, in fact, define this? This is a simulation only. Maybe it can be interesting for you. So if I open, in fact, image rotator defines, then I think it is here. So how this is a simulation only is defined is that it's very simple. We begin with synthesis translate off and we end with synthesis translate on. And between these two, in fact, I define this guy. Okay. Now, at the time of simulation, what will happen is that the Xilinx tool, your simulator, does not see this line, synthesis translate off. The simulator does not understand this line. So it sees this command, and this variable gets defined. And as this variable gets defined, this if comes true, and your model comes into play. But at the time of synthesis, synthesis translate off will turn off your synthesis engine. Consequently, this in fact definition will not be seen by the synthesis engine. Okay? And then synthesis translate on turns on the synthesis engine again. So at the time of synthesis, this variable is not defined. So if it is not defined, the one that comes true is this else. And this else, when it comes through, it causes the main, in fact, RTL of AXI Master Best IPIF to be instantiated inside your design. Okay, now I continue with briefly looking at the content of image rotator controller. This is kind of the most complicated module that we have in this design. And honestly speaking, it has taken some time for me to write this module. First look, if I look at the implementation, it's something near, I would say, something near 1,000 lines of Verilog code. Okay, just to have a correct implementation of this very basic rotation functions. 1,000 lines of Verilog code. And now, of course, some parts are comments. And now, but very little. And now I come, in fact, to the RTL. Okay, obviously, I'm beginning with the port list, and then as I described to you, I go to the main FSM, and then the main FSM, which is implemented here, is the guy who is responsible for controlling the overall operation of the module. What do I mean by the overall operation? I mean, it says read one block, write one block, read next block, write next block. So it generates this kind of control signals. It doesn't go into detail. It just controls the overall operation of my module. And then there are a set of counters which I have called receive and send block counters. As you remember, we divided the image into blocks of 120 by 120. And these are the counters which are indicating at each time of system operation on which block we are operating. Obviously, there are two counters on X direction and on Y direction, and obviously there are two categories: counters for receiving the image and then counters for writing the rotated image back. And then if I continue, I reach the part that I'm driving, in fact, those AXI IPIF related signals which have a fixed value. So the interface between my logic and the AXI Master IPIF, as I showed you, there are a set of signals. Now from these signals, there's some of them which are always fixed. They have a fixed value, and if I assign them to a fixed value, it's making my design really easier and more simple. So for example, the length of the transfer that we want to do is every time 240 bytes, as we described. So it's image block size, which is 120 multiplied by 2. Or we are always doing burst transactions, so the type is always 1. Or when I'm kind of doing the read operation, I'm receiving the data from AXI Master Bus IPIF. I am always ready to receive the signal. So I'm pretty sure my logic is designed so that whenever the data is coming, my logic can accept it, right? So this signal, master read destination ready, is always 0. And we never discontinue any transactions, so this other signal is always 1. And then I don't want to go into very detail right now, but there are other set of signals which are always driven by a constant value. And then next comes to the logic that I calculate the addresses in the DRAM memory from which I should read the pixels and to which I should write the pixels. This is the AXI address calculation. And this AXI address calculation obviously is done considering the block counters and considering the internal counters for each block. So based on these set of counters, I calculate for each, in fact, read transaction, for each write transaction, I calculate what is the physical address from which I should read to which I should write. And then comes the next FSM, which I call AXI Master FSM. So this is the second FSM of my design. And as I told you, this guy is responsible for handling the control signal and the flow of operation and data to the AXI Master IPIF. So this is the guy who is controlling when you really initiate the start of frame, when you for example, issue the next read or write request, and these sort of, in fact, tasks. So it has a it has a simple implementation. It's not really difficult. Basically, I can say this FSM is divided into two parts. One part is the logic, which is responsible for handling this interface when a read is being done. This is the read request part, as you see. And then the next part is the part which is responsible for handling this interface when the write is being done. And if I go inside each of these two parts, again, it is very simple. Basically, each of them have three phases. The first phase is the request sending phase. The second phase is to wait for the ACK, and then the third phase is to wait for the completion. And this is something I described to you. You request, the ACK comes, and then the data is transferred, and then the completion. And after the completion, you go to the next transaction. So the same is true for the write operation. Now, after this FSM, we come to the pixel buffer. And the pixel buffer is those 4 block memories that I described to you. They are responsible for receiving your pixels, saving your pixels inside, and then giving them back to you at suitable time. So there are the signal definitions and instantiation of block memories, 4 block memories that we need to keep those pixels. And then comes the logic, which is responsible for receiving the data from the AXI Master IPIF and putting this data into the block memories. So the AXI FSM that you saw there previously is responsible for managing the control interfaces, and then for data path, I have a separate logic which is responsible for receiving the data, input data part, and then another, in fact, logic which is responsible for grabbing the data out of the block memories and giving the data back to the IPIF, which is called output data. So the input data part is responsible for generating the right address for block memories, the address that each new coming pixel should be written to that address inside the block memory, and then the output data is responsible for generating the read address of these block memories, the address from which the pixels should be read. And now, in fact, when we are reading the pixels, it can be kind of a little bit tricky, especially when you are doing clockwise or counterclockwise operation. As I told you, when you are doing a 90-degree clockwise or counterclockwise operation, at the time of writing the pixels, you write each pixel to the block memory, but at the time of reading, what you do, you read 4 pixels just from one block memory and the next 4 from the next block memory. While, for example, at the time of performing a flip operation, you write 4 pixels to 4 block memories, and then again you read 4 pixels from 4 block memories. So the pattern that you perform reads and writes to block memories is different by the type of rotation that you do. And I have a logic along with the previous logic that I showed you that manage these situations. And then we have the logic that controls when we are reading, in fact, from the block memories. And finally, we have the logic which is creating the key signals between your logic and the AXI IPIF. So the logic that you see here, it's called master write source ready. And I described to you what this signal is. It's used when you have sent a write request, and now is the time to provide the data to the IPIF. So what this signal, what this logic is basically doing, it's looking at your AXI FSM, the state of your AXI FSM, based on that state, and obviously based on the status of your block memories which are providing the data to you, and based on the status of the IPIF, either it is it's ready to accept the data or not, it produces the source ready signal which is kind of indicative to the AXI IPIF that, look, I have put the data and you can grab it. So this is a piece of logic responsible for that. This is the piece of logic responsible for generating a startup frame. This is a piece of logic responsible for generating end of frame. And finally, this big piece of code that you see here is responsible for generating the correct data sequence, for sending the data to the IPIF. So this is our module. As you see, this logic is not simple. It's a big logic. It needs a lot of work. And now let's go ahead and perform some simulation and see the operation of this system. So here's my Vivado project. This guy here in simulation sources, if I open simulation sources, I have the test bench, and under the test bench I have the design under test. And as I told you, it's a kind of innovative method. The models that we use for simulation are not inside the test bench, they are inside the design itself. And through the technique that I described to you, this is simulation only. I enable or disable those models at the time of simulation. So here is the model that I use for AXI Slave block. It's actually very simple. It's giving fixed values to input image address, output image address. It receives the interrupt. It gives a fixed value for the begin operation, and then also it gives a fixed value for the rotation type. So for these signals, I just indicate a set of values. And this is the model for my AXI Slave block, and I think this is enough. And then there is the model for, in fact, AXI Master IPIF block. It's kind of more complicated. It resembles the operation of an AXI Master Burst IPIF block. By looking at the Xilinx documentation and also by looking at the real operation of the interface, in fact, between an AXI master and the AXI subsystem of ZYNQ, I have come into developing this module. It's not that complicated. It's not that simple. And I have tried to make it as accurate as possible. And also, this is the module which reads from a file at the time of providing data. So at the time of read that we want to read from the IPIF, what it does for the data, it reads a file and it puts the content of that file as the read data. I think it is here. So a file is opened. This file is basically an image. I will show you how I create this file. It's a text file. This is open. It contains the values for the pixels of the image. This file gets opened, and then the contents of the file at the time that my image rotator controller requests for data, the contents of this file, which are the pixels of that image, will be given to my, in fact, image rotator controller. And then when the image rotator controller performs its task and wants to write back the data, again, and this module receives the data and writes back that data into a file that then later I can convert it into an image and to see if the rotation has really done or not. Okay, so I can go ahead and perform a simulation and see if the module works correctly or not. So the input image that I'm giving at the current time to the simulation engine is this one. So this is the input image. It's very simple, just two circles, a rectangle. It's 100 by 120 by 120. So the simulation for now I do only for one block to make sure that only for this one block everything works fine. So this is the input image, and then I have a Python script. The Python script that I have created is responsible for reading this input PNG file, test_fig.png file. It reads this file and converts this file into a text file. And that's basically the text file contains kind of value for every pixel of the image. It's basically a grayscale image. So how does the Python script look like? If you're interested to know, it's the Python script. As you see, it is very complicated. We are using, in fact, the image processing toolbox of Python here. The operation is very simple. I'm reading the PNG file, and then I open the destination file, which is basically the text file, which will be later used at the time of simulation. And then what I do, I go through the pixels of this PNG file, and I take, in fact, right now only the first item of each pixel and write it to the text file. Okay. So since my image is at the moment black and white, that works fine. But it's very easily can be customized to have a full grayscale image. So I have this Python script. This Python script works on this test_fig.png and creates for me test_fig.txt. Test_fig.txt I open here inside my AXI Master plug model. I open here this file through the fopen Verilog system function, and then I read from this file through fscanf, and I give them at the time of the simulation to my image rotator controller. So later, then what I do is I write the received data to the out_fig.txt. So here is out_fig.txt, and then again I have another Python module which is responsible for reading this out_fig.txt and converting it into an image. And then I compare these two images, and these two images should be correct, meaning that the command that I have provided through my AXI Slave plug here is rotation CMD counterclockwise, is counterclockwise rotation. So I look at those two images, and that guy should be rotated counterclockwise 90 degrees. And this way I can check if everything is working fine. So here is again the Python module that is responsible for converting the text into the PNG file. Again, it's a very complicated piece of code. Okay, so I go ahead here for test. We can change this. For example, let's put clockwise rotation or whatever you like. These are a set of definition for the commands. These definitions are exactly the same everywhere in the design, in the RTL and in the simulation. So these are the definition for the commands that the CPU will give for the rotation to our hardware accelerator. So you can select any of them. Let's select, for example, horizontal flip, whatever. It's not important. We just put it here and we save it, and we run our simulation. So the simulation of Vivado starts, and we run for a while. For example, let's have it for 500 microseconds. That is done. The simulation is done, and here I have, in fact, complete set of signals between the image rotator and the AXI IPIF model, between the image rotator and the AXI slave plug, and then inside the image rotator. And I believe it's kind of good representative of what's happening in the real hardware. So what you see here, I see the block received and block sent command. So here is when one complete 120 by 120 block is received, and then here is when this 120 by 120 block is completely rotated and transferred to the destination. And then here we have, in fact, set of AXI signals which are used at the time of write. And then here we have set of AXI signals which are used. In fact, AXI, the set of IPIF logic signals that are used at the time of read. So this is when we are reading the block from AXI Master Best IPIF, and this is when I have done practically the rotation. I'm doing the rotation, I'm writing back the results to the AXI Master Best IPIF. So this is the simulation, and as I close the simulation here inside Vivado, I should have my file created. So what I do is that I check if my text file is updated. So here is my outfig. It should be updated. And now I can run this Python script and convert it into the output file. So currently the output file, this is the input file. I have not updated the output file yet. So I go ahead and I run my revolutionary Python script. So py and then Python and then py text to that's it. So now I should have the updated output image, and then I can also open the input image, and then we can see what has happened for this image, if it is correct, if it is not correct. Let's go back to Vivado and see what was the command. So it was horizontal flip rotation. So can we check if this is a horizontal flip rotation, if it is correct? Yeah, so this is how we validate our design, and I think the design is kind of ready to be implemented on the hardware. Obviously, I will add the ILA now so that if anything went wrong on the AXI interface, I can capture that and we can see together. Okay, that's the end of this simulation session. Thanks for watching, and soon I will come to you with a practical implementation of this module on the Z board or on the ZZ706. Thanks.